Right. So just to continue with the slide, it says that the heat dissipation. Now the statement says that the power transistors and other power devices must dissipate a large amount of internally generated heat, right? So what happens that if you have a power amplifier like this, okay, and so we can see that there is because of large amount of power delivered, okay, there should be some heat dissipation inside the transistor as well. And what happens that then it says that uh, uh, it is protected by an external heat sink. If you can see, it is protected by an external heat sink. So let me show you the picture of this. You can see some, okay, so this is a particular example of a power amplifier. You can see this is a power amplifier, remember this one, okay. Now this is a heat sink, remember, because of high heat dissipation, because of high power rating, heat is dissipated inside this, okay. So that is and that is taken out, or it is being neutralized by this heat sink. And remember, if you see, this is a heat fan as well, so to make the temperature normal. This was an experiment we did sometime in our studies, right, okay. So this is, you can see, this is infrared thermometer, okay, this one. So we have to check the temperature of the device every time it is operated. So this was to check the input and output behavior. You can see this is power amplifier spectrum, right. So this is almost, we call it like output frequency spectrum, right. We have we call this as the fundamental tones, and the IMTs, the intermode tones, right, okay. This is the power splitter actually, we can, or power combiner, and this is attenuator. We don't we are not concerned at this point how they works actually, but this is a real power amplifier testing system in a laboratory. So you can see this is the power supply you are using in high-tech laboratory. You can see there as well, okay. These are the signal generators, the same thing you find in high-tech university labs, right, okay. This is spectrum analyzer. Again, you can find this in high-tech lab as well. But the important point over here to mention is that because of the fact that power transistor dissipate heats, this is power amplifier, remember. So that heat is neutralized by this heat sink. So there are fins, like this one, see over here, okay. This is a heat sink, and still it dissipates a lot of heat to circulate that heat. So we apply an external fan, and this is an infrared thermometer check to see its temperature, the change in the temperature. So this is why these things are very important to know, that how actually power amplifier they works, right, okay. Next slide please. Okay, now over here it says that recall that the DC and the AC load lines intersect at the Q point. When the Q point is at the center of the AC load line, a maximum class A signal can be obtained. So okay, so this is the case of amplification, right, okay. This is you can see, this is what this is, a family of two lines, okay. This blue green line we call is AC load line, remember, and this one, the pink one, we call is the DC load line, okay. The DC load line, we know that the Q point is somewhere over here in the middle, okay, in the middle. So this is the midpoint, okay, which comes over here at this point, okay. And similarly for the current, it lies over here. So if our Q point, okay, Q point is our quiescent point. Q point is a point where we need to operate or amplifier. So if our operation is near to the center point, So we say that this is, we can get maximum amplification like this one, right? Good amplification you can see, or distortionless amplification. Okay, if we move around okay, on this DC load line, remember, towards the saturation point, okay, so we can have a distortion in the signal either in the positive half cycle or in the negative half cycle. And similarly, if the Q point is shifted over here towards the cutoff, again this will get distorted, right? Okay, so the optimum point is the Q point. So similarly, the AC load line, this is AC load line, okay, the green one. So we can also have an AC load line, okay, we define AC load line. Okay, now what is the difference between these two lines? Now the difference between these two lines is the DC load line operates, okay, when there is no actually input signal, like over here. Remember, over here the signal is there, you apply the signal, the AC signal, right? So the DC load line, remember, it depends upon your R1, R2 and VCC. So it depends upon the DC voltages and the resistors, right? Okay, so that's why we define or design our quiescent point Q. Okay, whenever we apply, okay, this input signal as shown in this figure, so then we have to draw the AC load line as well, right? Okay, so the AC load line means that it actually gives, it's a measure, or it is a parameter, or it is a check that how well this, or how good this input signal will get amplified at the output. So it is shown over here. If you see, this is the AC load line. So if the input signal over here, okay, this is the IC is the output, the input signal we say is IB. Remember, this was the IB input signal. So the operating point, if it is at the center, so we have a maximum swing. You can see a maximum swing over here, over here and over here. And for the output voltage, so this is output voltage and this is output current. So for both output current and voltage, we have a good equal swing. Okay, equal swing means that if this is a reference line, so the positive half cycle and the negative half cycle, basically they swing equally in positive and negative direction. So that's why we say this is a good measure, or a Q point gives us an indication. This Q point gives us an indication of how well your, or how good your amplifier is, right? Now if you see, this is a non-centered Q point over here. If you see, okay, if the Q point is closer to the cutoff, okay, this is the first case. So from here, okay, this was the Q point, which is the ideal Q point. It was centered over here. Now if it is moved towards this cutoff point, okay, so what would happen, that you can see that we have amplification. Okay, the output current, this one is the output current, this one is the output voltage. So for a small signal there is no effect, so the variation is very small. But if for a large signal, if you see the signal over here, for a large signal, if the magnitude amplitude gets increased, okay, so there is a clipped at this position over here. Likewise in the output voltage over here, okay, there is a distortion or clipping at the cutoff. Okay, so this is the same thing. It happens if I move this cutoff point. Remember, if I move this cutoff point from the center towards the saturation, this is saturation point. Okay, so closer to the saturation, this was my ideal Q point at the center. Okay, closer to the saturation, okay, for small signal there is no distortion, okay, but for a large signal now, now this part is getting distorted. Okay, the positive half cycle of the output current and the negative half cycle of the output voltage get distorted.